According to National Electrical Code Section 225.32, an outside feeder to more than one building or structure generally requires a disconnecting means, essentially a main breaker, in the distribution panel serving the remote building. However, there are exceptions to this rule. Understanding these exceptions can save on equipment costs and simplify electrical installations, especially in industrial settings with multiple buildings on the same site. The specific exception relevant is exception number 1. This exception states that a disconnecting means is not required at the remote building or structure if certain conditions are met. These conditions are designed to ensure safety and control over the electrical system even without a local disconnecting means. Firstly, the feeder must originate from a disconnecting means located on the premises. This means that the feeder must be supplied from a breaker or switch within the property limits of the facility. The location of this disconnecting means is crucial. It ensures that personnel on site have control over the power supply to the remote building. Secondly, the feeder must be protected by an overcurrent device located on the premises. This overcurrent device, typically a breaker, is intended to protect the feeder conductors from overloads and short circuits. It must be situated within the property limits, providing a means to quickly de-energize the feeder in case of a fault. Thirdly, the feeder must be under single management. This condition implies that the entire electrical system, including the feeder and the buildings it serves, is under the control of a single entity or management team. This ensures that there is a clear line of responsibility and accountability for the operation and maintenance of the system. Fourthly, a safe switching procedure must be established and followed. This is a critical requirement. The safe switching procedure should outline the steps to be taken when energizing the feeder for maintenance, repairs, or other purposes. It should include lockout-tagout procedures to prevent accidental re-energization of the feeder while work is being performed. Let's elaborate on each of these conditions. The requirement that the feeder originates from a disconnecting means located on the premises is fundamental to ensuring control over the electrical supply. This disconnecting means allows personnel to quickly and safely de-energize the feeder in case of an emergency or for planned maintenance. It should be readily accessible and clearly labeled to facilitate its use. The overcurrent protection requirement is equally important. The overcurrent device protects the feeder conductors from damage due to excessive current flow. The size of the overcurrent device should be carefully selected to match the ampacity of the feeder conductors and the load served by the distribution panel in the remote building. Using an appropriately sized breaker is crucial for safety and code compliance. The single management requirement is intended to ensure that there is a clear line of authority and responsibility for the electrical system. This is particularly important in industrial settings with multiple buildings or structures. Single management allows for coordinated operation and maintenance of the electrical system, minimizing the risk of errors or accidents. The safe switching procedure requirement is perhaps the most critical of all. A well-defined and strictly followed safe switching procedure can prevent accidents and injuries during maintenance or repair work. The procedure should include detailed steps for de-energizing the feeder, verifying that it is de-energized, and locking out and tagging out the disconnecting means to prevent accidental re-energization. Lockout-tagout is a safety procedure that involves placing a lock and a tag on the disconnecting means to indicate that it is not to be operated. The tag should identify the person who placed the lock and the reason for the lockout. This prevents someone from inadvertently re-energizing the feeder while work is being performed, potentially causing serious injury or death. In summary, to determine whether a main breaker is required in the distribution panel of the remote building, you must carefully evaluate whether all four of these conditions are met. If the feeder originates from a disconnecting means on the premises, is protected by an overcurrent device on the premises, is under single management, and a safe switching procedure is established and followed, then a main breaker is not required. However, if any of these conditions are not met, then a main breaker is required to comply with the NEC. It's important to note that this exception is not a blanket waiver of the requirement for a disconnecting means. It is a conditional exception that applies only when the specified conditions are met. Furthermore, even if the exception is applicable, it may still be prudent to install a main breaker in the distribution panel for convenience or enhanced safety. A main breaker provides a local means of disconnecting power to the distribution panel, which can be useful for troubleshooting, repairs, or other purposes. The decision of whether or not to install a main breaker, even when it is not required by code, should be based on a careful assessment of the specific circumstances and the needs of the facility. Always consult with a qualified electrical engineer or contractor to ensure compliance with the NEC and to make informed decisions about electrical system design and installation. Remember to keep safety as the #1 priority when working with electrical systems. Always follow safe work practices and use appropriate personal protective equipment. Electrical work can be dangerous, and it is essential to take all necessary precautions to prevent accidents and injuries. Regarding the National Electrical Code, it is a comprehensive set of standards that govern the safe installation of electrical wiring and equipment. It is updated every 3 years to reflect the latest advances in technology and safety practices. The NEC is adopted by most states and local jurisdictions in the United States. Compliance with the NEC is essential for ensuring the safety of people and property. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is a complex document, and it is important to have a thorough understanding of its requirements before undertaking any electrical work. There are many resources available to help you learn about the NEC, including training courses, online tutorials, and publications from the National Fire Protection Association, which publishes the NEC. Understanding the NEC is critical for anyone involved in the design, installation, or maintenance of electrical systems. It helps ensure that electrical work is performed safely and in accordance with accepted industry standards. Failure to comply with the NEC can result in fines, penalties, and, more importantly, increased risk of electrical hazards. So, whether you are an electrician, engineer, contractor, or simply a homeowner, it is important to familiarize yourself with the NEC and its requirements. The exception discussed allows for flexibility in certain situations, but it also places a greater emphasis on proper planning, coordination, and safe work practices. Make sure to thoroughly evaluate all aspects of the installation before deciding whether to rely on this exception. Again, safety is paramount, and any decision should prioritize the well-being of personnel and the protection of property. Now let's delve deeper into each of the requirements mentioned. The feeder originating from a disconnecting means on the premises ensures that there's a readily accessible way to energize the entire feeder. This is crucial in emergency situations or for planned maintenance. The disconnecting means should be clearly labeled and easily identifiable. It could be a circuit breaker or a fuse disconnect switch, depending on the application and voltage level. It's essential that the disconnecting means is rated appropriately for the feeder's voltage and current carrying capacity. The overcurrent protection on the premises protects the feeder conductors from overloads and short circuits. The overcurrent device, typically a circuit breaker or fuses, must be sized according to the ampacity of the conductors and the characteristics of the load being served. The National Electrical Code provides detailed guidelines for determining the appropriate size of overcurrent protection devices. Correctly sized overcurrent protection is vital for preventing conductor damage and potential fire hazards. Single management ensures that there's a clear line of authority and responsibility for the electrical system. This is particularly important in large industrial facilities with multiple buildings and electrical systems. Having a single management structure allows for coordinated operation, maintenance, and emergency response. It also facilitates the implementation of consistent safety practices and procedures across the entire facility. A safe switching procedure is perhaps the most critical element. It outlines the steps that must be followed when energizing and re-energizing the feeder. The procedure should include lockout-tagout procedures to prevent accidental re-energization while work is being performed. Lockout-tagout involves physically isolating the disconnecting means and attaching a lock and tag to prevent it from being operated. The tag identifies the person who placed the lock and the reason for the lockout. A safe switching procedure should also include verification steps to ensure that the feeder is indeed energized before any work is performed. This can be accomplished using a voltmeter to measure the voltage on the feeder conductors. The safe switching procedure should be documented and readily available to all personnel who may be involved in operating or maintaining the electrical system. Regular training should be provided to ensure that personnel are familiar with the procedure and understand its importance. It is also important to review and update the safe switching procedure periodically to reflect changes in the electrical system or work practices. The absence of a main breaker in the remote building places a greater emphasis on the reliability and effectiveness of the disconnecting means and overcurrent protection at the source. It also underscores the importance of a well-defined and rigorously enforced safe switching procedure. While the exception in NEC 225.32 provides flexibility, it should be applied with careful consideration and a thorough understanding of the potential risks. Remember that the primary goal is always to ensure the safety of personnel and the protection of property. If there's any doubt about whether the exception is appropriate, it's always best to err on the side of caution and install a main breaker in the remote building. The cost of the breaker is relatively small compared to the potential consequences of an electrical accident. Also, local amendments to the NEC might apply. Always check with your local authority having jurisdiction. Before applying this exception, consider the practical implications of not having a main breaker in the remote building. For example, how would you isolate the distribution panel for maintenance or repairs? Would you have to coordinate with personnel in the main building to de-energize the feeder? How would you respond to an electrical emergency in the remote building? Having a main breaker in the remote building provides a convenient and readily accessible way to isolate the distribution panel, which can be particularly useful in emergency situations. Also consider the potential for future expansion or changes to the electrical system. Adding a main breaker later could be more difficult and costly than installing it during the initial installation. Finally, remember that the decision of whether or not to install a main breaker is ultimately a matter of engineering judgment. There may be situations where the exception applies, but it's still prudent to install a main breaker for enhanced safety or operational flexibility. The key is to carefully evaluate all aspects of the installation and make an informed decision that prioritizes safety and reliability. Let's consider a more practical example. Imagine a manufacturing plant with a main building and a separate warehouse building. The plant wants to install a feeder from the main switchboard in the main building to a distribution panel in the warehouse building. The feeder will supply power to lighting, receptacles, and some small equipment in the warehouse. The plant is under single management, and they have a well-established safe switching procedure. The feeder originates from a circuit breaker in the main switchboard, which is located on the premises. The circuit breaker is sized appropriately to protect the feeder conductors and the load in the warehouse. In this scenario, the plant could potentially rely on the exception in NEC 225.32 and not install a main breaker in the distribution panel in the warehouse. However, they should carefully consider the implications of this decision. For example, if there's an electrical problem in the warehouse, they would have to coordinate with personnel in the main building to de-energize the feeder. This could delay the troubleshooting process and potentially disrupt operations. Also, if they plan to add more equipment to the warehouse in the future, they may need to upgrade the feeder and the overcurrent protection in the main switchboard. Adding a main breaker in the warehouse at that time could be more difficult and costly than installing it during the initial installation. Ultimately, the decision of whether or not to install a main breaker in the warehouse should be based on a careful assessment of the plant's specific needs and circumstances. They should weigh the cost savings of not installing a main breaker against the potential inconvenience and safety risks. It's always a good idea to consult with a qualified electrical engineer or contractor to get their professional opinion. It is also important to consider the voltage drop on the feeder. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and can also reduce the efficiency of the electrical system. The National Electrical Code provides guidelines for limiting voltage drop on feeders. The length of the feeder and the ampacity of the load being served will affect the voltage drop. Using larger conductors can reduce voltage drop, but this will also increase the cost of the installation. It is important to carefully calculate the voltage drop and select conductors that are sized appropriately. Proper grounding is also essential for electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protection device and clear the fault. The National Electrical Code provides detailed requirements for grounding electrical systems. The grounding system should be properly installed and maintained to ensure its effectiveness. Regular inspections and testing of the grounding system are recommended. Surge protection is another important consideration. Surges are transient overvoltages that can damage or destroy electrical equipment. Surges can be caused by lightning, switching operations, or other disturbances on the electrical system. Surge protective devices, or SPDs, can be installed to protect equipment from surges. SPD should be selected based on the voltage and current levels of the electrical system. The National Electrical Code provides guidelines for the installation of SPD.